My name is Paul Ganssle. I'm a software engineer at Google. I'm also a prolific contributor to open source, so I maintain things like setup tools and datautil, and I'm a core developer of the Python language. And this talk came about because I wanted to write a backend for datautil to kind of speed it up in Rust. And there were kind of a lot of options, and none of them had any native support for datetime. So of course, I ended up like adding a whole bunch of extensions for datetime into the PI3 library, because that's how things kind of spiral in open source. So I figured I would try and get some of my thoughts together and give it as a couple talks, just so other people don't have to make my mistakes. One caveat I'd like to start with is that there's a lot of code. It's very code heavy, and a lot of the code is in Rust. So don't worry, you don't really have to be concerned with what the code says or whether I coded it right. Because just like look at the syntax highlighting and let it wash over you if you're feeling overwhelmed, because it's mostly there for reference, and these slides are available on GitHub, so you can just like look at them and critique me on Twitter. So you've probably been to some of my talks before, or you may have been to some of my talks before, and they're like very lighthearted, but this one is not. It's just purely educational. So if someone could lock the doors. But seriously, that is the last joke. All right, so one thing that I'm sure we all like about Python, or something you may have heard about Python, is that it is really good glue language. It is kind of like coding in pseudocode. You just write what you want, and it's super easy to work with. You get really fast developer cycles, but it can be slow sometimes. But you can get a lot of the benefits of Python's high-level features without its downsides if you use it as a glue language. And in fact, a lot of the most important things in the Python ecosystem are actually just glue around libraries written in other languages. So you have like NumPy, SciPy, scikit-learn. These are all Python wrappers that provide a nice high-level API around super optimized scientific code written in like C or Fortran or whatever. OpenCV, TensorFlow, PyTorch, Pillow, which is for imaging. In fact, the standard library itself, a huge fraction of it is written in C, and you always access it through nice, safe, easy to work with Python. So that's one reason why Python is a great glue language. If you're writing extensions or just kind of gluing together compiled code, I'm just going to use this example. It's the sieve of Eratosthenes. It's a very simple algorithm. And what it does is you give it a number, and it outputs a list that has all the prime numbers less than or equal to the number you gave it. So here's what it looks like in Python. It's like 10 lines. It's quite simple. I'm not going to go into what the algorithm does. Here's what it looks like if you write that same thing as a C extension. So if you use the C API, you'll notice that the code on this slide is a little bit smaller, because even though I use this like terse way of programming where the for line is all on one line, it still wouldn't all really fit on one slide. Because it's quite verbose. And in fact, most of the logic is just right here. It doesn't look that different from the Python logic, except that you have this error handling up here and memory allocation, and then you do the logic, and then you have to convert all this stuff into Python objects and allocate a list, and you have to check for exceptions. And these are all things that the Python interpreter kind of handles for you. So why would you even bother writing something like this, where you have to do free and you have a goto in there? I mean, really, goto. But the reason is performance. So if you use the pure Python version of this function, you get something that takes 526, or if you use the C version of it, you get something that takes like 526 microseconds. If you use the pure Python version, it's something like almost 20 milliseconds. And once you get past the function overhead, you're getting, like the function call overhead, you're getting something like a speed up of like 40 times by using C. So when you want speed, you use the C API. But C has some pretty serious downsides. The manual memory management we talked about. You have to do manual reference counting. And C is not a memory-safe language, so all the like cryptography people and security people are like cringing whenever they have to write any C, for good reason. Because in the original version of the code from the previous slide, and I was tempted to leave it in here, I wrote it like this, because every time you write a for loop, you go, oh, I'll just iterate from 0 to n, because that's how many elements there are. But in the sieve of Eratosthenes, it's a lot easier if you start your array at 2, because 1 is not a prime number. And so the length of this is not actually n, but it's n minus 1. But C did not complain. And in the original version of this, what it would do is it would say, all right, I'm just going to grab 5 things, and then I'll just grab whatever memory happens to be one past the end of the array, and I'll just turn that into a Python object. So you get like 2, 3, 5, 82. And it's like, OK, I guess. And C did not complain about this. And maybe you're like a genius programmer, and you don't need these comments saying like, hey, guess what? You made a mistake. But those comments don't come standard. And I would have, I did, in fact, miss that error. So that's where Rust comes in. Rust is sort of a competitor to C, or it's at least aiming towards the same systems programming niche that C and C++ are currently dominating. And it has useful language features that try and bake into the language itself the concepts of memory safety, fearless concurrency, while keeping high performance. And something that's going to be very interesting for Pythonistas is that it also has a broad, inclusive community with a large open source ecosystem. So you just go on Cargo or on Crates, and you can just cargo install stuff. And people are very actively developing this at the moment. It's a very hot language. So I thought before we go on too much, I would give you some feel for what it's like to program in Rust. And one important concept, because I can't really give you a whole tutorial on Rust, but one important concept is ownership. So in Rust, variable bindings have ownership over the resources that they're bound to. So in this case, we have this variable v, and it's bound to this vector. So that vector is going to allocate that's going to allocate a vector, and then those resources have to get deallocated at some point. And what we're saying here is that when v goes out of scope, because v owns those resources, you can free those resources as soon as v goes out of scope. So that's fairly simple in a single function, but if you say bind v here, and then you pass it to this function that's taking ownership of v, and then that function has now bound it to this other thing, which I also called v. I'm sorry about that. Once that one goes out of scope, you should be able to clean it up. And in fact, that's how it worked, because this function took ownership of these resources. So once this function is done executing, those resources are deallocated. So in C, if you try to do something like this, that would be like a use after free error, because at the end of this function, you've implicitly freed all the resources behind the vector. But in Rust, the compiler will not let you do this. This is the fabled borrow checker, right? Or maybe it's not, I don't know. Anyway, but it's also, if you'll notice, I put in these comments to be like, yeah, the comments, they don't come standard, right? In Rust, the comments actually do come standard, because if you'll notice, the compiler automatically generates things saying, oh, here's where you created this, here's where it was moved, and then here's when you tried to borrow it later. So it actually tells you exactly what I put in those comments without the comments. If you just listen to the compiler, it will eliminate huge classes of bugs, including like most memory safety bugs. So I guess that's one of the takeaways of using Rust, is that if you use Rust and you can get it to compile, which is kind of an if, you are not necessarily saying that you have a good program or one that even really works, but it does eliminate huge classes of bugs, which are important for security. Rust also lets you circumvent these rules with like unsafe blocks, and the important thing about those unsafe blocks is that yes, certain things that will violate these ownership rules can occur within those unsafe blocks, but that's the hottest part of your interface, right? Most of the code is not in an unsafe block, and you know to focus your auditing efforts on the unsafe parts of the code. OK, so we know a little bit about Rust. We know why we may not want to use C. So how can we use Rust to write our Python extensions? There are two main approaches. The first one I'm going to talk about is the PI3 approach, which is writing Rust API bindings. This is the equivalent of the C API. And in fact, it's just Rust wrappers around the C API. So here's an example of some bindings written in Rust. I have my Civa Veritasnes. I wrote it in pure Rust just to make it more obvious what this would look like if you were binding to something that was originally written in Rust. So I have this Civ implementation, and then this part exposes it to Python. It says, all right, here just take an integer from Python, and you're going to return a list, and then call this function, pass it my integer, and then return a list from it. So this part with the py list and this little macro that does some wrapper stuff, that handles all the chunks of C code that handle all the reference counting and the memory management and stuff like that. And how does it perform? It performs basically the same as the C API in this particular case. So here you can see that it works the same. And when we compare them, in fact, this Rust version happened to be a little bit faster, but that's like clearly within the noise of the function. So I'm just going to say that they take the same amount of time. The way it works is that PI3 is divided into 2 layers. The lowest layer, the one that you should probably not be interacting with, is the FFI layer. FFI stands for Foreign Function Interface. So what this does is it writes some, like Rust has the ability to interact with C using like foreign functions. So here you're just declaring some functions that you're saying, oh, this is a C function. And eventually what we're going to do is we're going to bind to libpython.so, and it's going to say it's going to find this function object. It's going to find this function object, and you can call it from Rust. So I have this on the FFI layer. You wrap all the functions, and then you declare all the data structures. You have to declare the exact same data structures as they are represented in memory. That's what this, I think, wrapper C or something like that. And then finally, all the macros. This is the most annoying part. Is all the macros in C, those don't translate, so you have to just manually rewrite the macros if you want the same API. So once you have all that stuff, and this is all like super unsafe, right? Pub unsafe. This is like a C data structure. This is unsafe extern C. That's just calling C functions. Once you have that, PI3 has another layer, which is the safe Rust layer. So it has these structs, and it has these interfaces where you say, all right, this is my safe Rust type, and it's called PyDate. And its implementation, like the implementation of the constructor and the implementation of from timestamp and the implementation of these data accesses, they may call unsafe Rust and manipulate raw pointers under the hood. But assuming we did this right, you can now just treat this as regular Rust, and and the code that you write should be safe. So it has all the guarantees of Rust, premised on the fact that PI3 was written correctly. But PI3 is one place for everyone to audit, and everyone who could use it at least gets the benefits of any bugs you fix there. So once you have, so here's how it looks if you want to actually use it as a user. You have these little things. They're procedural macros, but you can just call them decorators because they basically act like decorators. So you have you have this py function macro, and here I've written a function called seconds before, and what it does is it takes one of these PyDate objects, and it takes a number of seconds, and then it says, just give me the date that was this number of seconds before the date that you told me, right? It's like just subtract this number of seconds. And then I declare a module by putting some initializer function, and then I add the seconds before. And when I compile this and I call it from Python, it has this module called dateEX, and when I call seconds before, it actually goes back and it calculates the right number of seconds before. What's interesting is that if you'll notice, I don't really have any error handling here. Like the constructor itself also didn't really have any error handling in the date constructor. That stuff is all handled at the C level. The only nod to error handling here is that I have this. I'm returning a py result instead of a raw py date. And that's basically enough, actually, which is that when you try and unwrap this py result, it will propagate the errors correctly. So if I try and do something where I say, oh, here's the first possible date, give me a million seconds before it, it'll say, oh, we failed to construct this, year 0 is out of range, and the exception just kind of work. So it's quite nice that way. You can also make a class. You just have a Rust struct, and you declare it to be a class, and you can put methods on it. You can have a constructor for it. And then you, again, put it into a module. I call this module classy. And then you can import your point, and you can do things like construct these, and you can call this Rust method from Python. And it just kind of works. So that's very useful. The other approach is to use C FFI bindings. So these are, again, foreign function interfaces. And this does the FFI in reverse. So in PI3, the FFI stuff was all buried in the Rust, and then and you're calling Rust functions, which are then calling the Python C API. This goes kind of the other way. This says, like, forget about Python entirely. What we're going to do is we're going to take our Rust stuff and we're just going to translate it not into Python, but into the lingua franca of programming, which is C, which is C foreign functions. So what we do is we have the same implementation of the civ of Eratosthenes, but instead we have this like no mangle pub unsafe extern C function that has these like mutable raw pointers. This is like the most unsafe Rust that you could possibly see. And in fact, like this part says, once we're done with this function, whoever took the result of this, they're managing the memory now. So don't even let Rust manage the memory anymore. And because of that, because there's a combination of two things. One, this returns a vec. So Rust is the only one who knows how to deallocate the vec. And it's also saying, please don't deallocate this vector. We also have to pass a function to whoever's going to get the result of this, and that lets them deallocate it. But this is actually fairly simple. And one huge benefit of this is that none of this is Python specific. So you could write the Python bindings around this, or you could write JavaScript bindings, Ruby bindings, pretty much anything that has access to CFFI, which is almost every language. So this is kind of a universal interface. And in Python, you can use milksnake to make this much easier. Milksnake will generate this native FFI and lib, and under the hood, it uses a module called CFFI. And what you end up doing is some of that memory management that you saw in the original C API code, you're just doing it in pure Python. So here we're like allocating some memory, and then we pass the memory to our civ function over the CFFI. And then here I'm just copying it over to a list, and then I deallocate the original array, and I can return the list. And when we time it, it actually turns out to be like a little bit slower than PI3, but I actually picked this example in a specific way, which is that for anything that just returns like integers or whatever, this looks pretty much the same as PI3. It's only when you're working with Python-specific types like lists and date times and stuff that you need to do any kind of interesting stuff with CFFI. So this is a little bit unfair, but I was trying to highlight the difference. Okay, so far I've told you how we can do this, but we haven't really talked about too much about if you should do this, because right now I'm just saying like Rust is great, it has all these memory safety features, but there's another language that has memory safety features, which is Python. And it turns out you can get like compiled backend code out of something that looks a heck of a lot like Python using Scytheon. So Scytheon, you just sort of write this pseudocode, and in this case, what I've done is I have it set up so that this pseudocode will generate C++ under the hood, and it'll generate a C++ vector. And I just write this function, and it looks pretty similar to the original Python function I wrote, except that I'm doing a little bit more stuff where I'm declaring types, right? And once that's done, I do my build step. It generates C++. The C++ gets compiled, and then I have a backend. So now, if we compare the pure Python to the C extension to the Scytheon, we're looking at something that's, okay, a little bit slower. It's like 3 times slower than the handwritten C function, but it's also like almost 10 times faster than pure Python. So, I mean, how fast do you really need to go? So this is probably like way more mature than either of the other 2 approaches I showed. It may be a little bit slower, and it doesn't help in the case where if you're trying to like bind to an existing Rust library. But it's something you really want to keep in mind, because you can't just be like, you can't just have the goal be, I'm going to write some Rust stuff, even though half the people in this room, that's your goal. Come on, admit it. All right, so what do we choose? So if we're looking at just speed on my like totally skewed benchmark, which was designed to make milksnake look bad, you can see that essentially, order of magnitude, PI3 and milksnake do about the same. They do about the same as the C API. Scytheon is a little bit slower than the compiled stuff, but it's a lot faster than pure Python. And one thing I'll say is, like, don't take this chart too seriously. Obviously, I've mentioned it's not a representative benchmark, but also I don't know that I'm the best person at writing Scytheon. I haven't written too many Scytheon things, and I certainly don't write Civil Eratosthenes that much in my day job, though I do work at Google, so I did have to pass that interview. Man, I'm so sorry I lied to you. There's way more jokes in this than I remembered. So anyway, the point is, I wouldn't take this too seriously, but order of magnitude, it essentially comports with my pre-existing understanding of how this would work. So in terms of which thing you should choose, there's pros and cons of, if you're going with Rust, whether you should use the CFFI or the PI3 method. CFFI or milksnake. Milksnake is basically just a helper for the CFFI. The pro is it's more portable interface because you can use it on like any language. The Rust dependency itself is actually much smaller because you don't have to pull in all these bindings for Python. So if you care about a difference in 5 megabytes in your binaries. And I'm told that CFFI style stuff is a lot easier for PyPy to optimize over. So if you're using PyPy as your interpreter, the CFFI stuff will work a lot better, and it will also probably be faster. The cons, you have a runtime dependency on milksnake and CFFI. It does not have any native support for any of these Python-specific types, tuples, datetimes, lists. So you're going to be doing a lot of boilerplate code in your Python, which is better than doing it in C. And it may require memory management in Python, which doesn't really have the huge advantage. And the biggest con for me is that the interface, the public interface, the one that you're maintaining, is in unsafe Rust, right? Because you have to write all these pub function things. You have to get all that stuff right. But of course, that still means if most of your backend is written in Rust, that interface may be a fairly small part of your surface area. For the API, the benefit is that most of your writing safe Rust. It has no runtime dependencies. It can work directly with the Python containers and objects from the standard library. It can also easily call Python from Rust. And it manages the GIL and reference counts, and it has a lot of abstractions around that. The cons, it requires nightly Rust, which some people, especially people who have certain packaging requirements, find to be onerous. I've never found it terribly onerous. Its API is actually still quite unstable. It's like properly zero var, so it's like 0.7.0, and it like breaks all the time. I mean, it breaks the interface for very good reasons all the time, but that does mean it's improving. I don't know about these last two. When I first wrote it, when I first wrote this talk, I thought that it could really use speed improvements, and it was still quite buggy, but it's getting much better all the time. So I have a little bit of time to just say where I think the Rust ecosystem could go here, or the Rust Python ecosystem could go. One is that a lot of the downsides of the milksnake approach are fixable. Not that the public interface is in unsafe Rust, but like all this like crazy memory. Well, actually, even that part, right, is you could write you could take these kind of crazy looking things where you're manipulating those and turn them into procedural macros, so that in the end you just write something like that and it would generate this code for you as part of your build. So you can actually get a lot of those advantages using the CFFI approach, but you have to someone has to write this library. There is also an equivalent library that you could write, and probably the same library in Python, right, that handles all these like crazy allocation and deallocation for you, assuming that you're using the FFI wrappers. But I mean, I'm not going to write that project. Hopefully, one of you will. And then the last opportunity for improvement is that like this is PI3 is a very active project. Stuff is getting merged all the time. First time I gave this talk, I took a screenshot because something had been merged 23 minutes before the talk. I'm not a committer. I don't have any rights on this project, so I can't say that I'll merge your stuff. But if you want me to review your pull requests, or if you want any advice on how to contribute to PI3, I have contributed a decent amount, like 40 or 50 commits to this library, so I kind of know the code base, and I'm definitely willing to help. So, all right, thank you. That is the end of my talk.